Okay, in this problem we're being asked to calculate the power associated with each of two resistors that are in series with one another. I could think of a number of ways to solve this problem. We could combine those two resistors into a single equivalent resistor. We could use voltage division. It turns out that in this problem we've been asked to, first of all, calculate the voltage across each of the resistors, so that suggests that we should go ahead and use voltage division. Now, half the battle in a voltage division problem is labeling everything sufficiently, so I'm going to go ahead and label the voltages. I can see that because the positive terminal is on the top here, the current is going to tend to flow clockwise, which is why I've put the positive sign on this voltage on the top, and then I'll do the same thing down here, V sub 5 ohms, positive on the top, negative on the bottom. Now, voltage division is going to allow us to calculate these voltages in a fairly straightforward manner. The 15 ohm voltage is going to be the total voltage, 10 volts, multiplied by the ratio of the voltage that the resistor that we care about, divided by the sum of the two resistances. And this works out to be 7.5 volts. Now, I could go ahead and just assume that the other 2.5 volts is going to drop across the 5 ohm resistor, but as a good engineer, I'm going to go ahead and calculate that separately, and then that will allow me to double check my work to make sure that they do in fact add up to 10 volts. Numerator, again, is the resistor that I care about. In this case, that's 5 ohms. So I have 15 plus 5 in the denominator. And when I do that calculation, I do, in fact, get 2.5 volts. So it's reassuring to see that those two voltages add up to the total voltage of 10 volts. It suggests to me that I probably haven't made a mistake. I also see that the larger resistance of 15 ohms is getting the majority of the voltage. And so that's what I would expect in voltage division. Now, the power that's being consumed by the 15 ohm resistor is going to be the voltage across the 15 ohm resistor squared divided by the resistance of the 15 ohm resistor. And so this is going to be 7.5 volts squared divided by 15 ohms, and this works out to be 3.75 watts. And then the power that's being consumed by the 5 ohm resistor is going to be the voltage across the 5 ohm resistor squared divided by the resistance of the 5 ohm resistor, which is going to be 2.5 volts squared divided by 5 ohms, which turns out to be 1.25 watts. Now, ordinarily, we'd be done with the problem. We've calculated the voltage across each of those two resistors. We could easily calculate the current through either of them. Notice, though, that the shortcut that we used meant that we didn't need to know the current. The current is sort of implied in the shortcut equation that we used. But part B of this equation, we're asked to then repeat this calculation by then calculating the current through each resistor, and then we can use the opposite shortcut of the one that we just saw above. So if I'm going to do this, I can see that the 15 ohm and the 5 ohm resistors are going to be in series, so I'm just going to go ahead and redraw the circuit with the equivalent resistance of 20 ohms. Remember that resistor is in series, you simply add their resistances. So there we have 20 ohms, and I still have the same 10 volts here, and there's going to be a single current I flowing down through that resistance. So now to calculate that current I can see that I is going to be equal to the 10 volts divided by the 20 ohms, which in this case is 0.5 amps, and that the power being consumed by the 15 ohm resistor is I of the 15 ohm resistor squared multiplied by the resistance of the 15 ohm resistor, which is 0.5 amps squared times 15 ohms, which is 3.75 watts. And that the power that is consumed by the 5 ohm resistor is going to be the current through the 5 ohm resistor squared times the resistance of the 5 ohm resistor, which is 0.5 amps squared times 5 ohms, which it turns out is 1.25 watts. And what we can see when we zoom back out and compare the answers is that we get the same we get the same power, 3.75 watts, regardless of which method we use for the first resistor, and 1.25 watts, regardless of the method we use for the second resistor. What this really shows us is an example of something you're going to see as we move forward. There are going to be many different ways that we can approach solving these problems. As your toolkit gets to have more and more tools in it, you can make decisions about which way you want to solve each problem, but every method has to give the same result. If they're all equally valid and there is one correct answer, every method has to give the correct answer.